Imagine trying to find, like, the 50 largest items in a group of 2 billion records. Or picture trying to locate the non-zero items that represent less than 0.1% of this impossibly huge collection of data, and you have to do it in milliseconds. Every single time you open an app on your phone, a system somewhere is performing this exact magic trick.
Yeah, I mean, it sounds like a mathematical riddle, right? But it is literally the foundational reality of the modern internet. You just cannot build a massive global application without solving that specific needle in a haystack problem at petabyte scale.
Welcome to today's deep dive. We are looking at a pretty hefty stack of sources today.
Very technical.
Very. And our mission today is to demystify HBase. We are going to translate these dense distributed computing manuals into a real exploration of how massive apps actually manage their oceans of data and, look at the underlying mechanics of scaling technology to a global level.
To kind of set the baseline here, HBase is an open source, non-relational distributed database. It is written in Java, originally developed by a company called PowerSet, and it's heavily modeled after Google's Bigtable.
Right.
And crucially, it sits right on top of a foundational layer called HDFS, which is the Hadoop distributed file system.
Okay, let's unpack that architecture for a second, because understanding the difference between HDFS and HBase is pretty crucial here.
Absolutely.
HDFS is essentially just a giant decentralized hard drive. It takes massive files, chops them into blocks, and then scatters them across thousands of commodity computers.
Right. It's great for storing petabytes of data securely, but it is fundamentally dumb.
Exactly. Like, if you ask HDFS to find one specific user's profile, it literally has to scan every single block on every single machine. It is a storage system, not an index.
And that is exactly where HBase comes in. HBase provides the brain on top of that dumb storage. It builds this real-time random access database over those scattered files.
So it knows exactly where things are.
Yes. You ask HBase for a user profile, and it knows exactly which machine, which disk, and which sector holds that specific data, and it retrieves it in milliseconds.
And it does this specifically for what the texts call sparse data. I kind of visualize this as an impossibly large spreadsheet. We are talking billions of rows and millions of columns.
A massive grid.
Right, but 99% of the cells in this spreadsheet are completely blank. There's just nothing in them. But you need to retrieve the few cells that actually have data without scanning billions of empty boxes.
Yeah, and traditional databases really struggle with that level of emptiness.
Right.
A classic relational database wants to allocate space and, strict structural rules for every column you define, even if it's empty.
Which is a huge waste of space.
Exactly. HBase avoids that by only storing the cells that actually contain a value. So if a column is empty for a specific row, it literally takes up 0 bytes of storage. It just doesn't exist for that row.
I mean, it is brilliant for empty space, but you don't build a massive distributed architecture just to run a sparse spreadsheet. What kind of modern application actually generates data that looks like this?
Well, think about user telemetry or behavior tracking. For example, Airbnb uses HBase as part of its Airstream real-time stream computation framework.
Oh, wow.
Yeah, and Netflix and Pinterest use it. Spotify relies on it to feed their machine learning jobs. Inger uses it to power their entire notification system.
That is a lot of heavy hitters.
It is. Because when millions of users are taking highly specific, isolated actions like liking a photo, pausing a video, adding an item to a cart, you generate this massive wide data set where most users haven't taken most actions. That is the exact definition of sparse data at scale.
Okay, I understand the scale, but I keep coming back to the database itself. If this is managing structured data, why not just use a classic SQL database?
Right.
I mean, we have had SQL for decades. It is a proven, reliable technology. Why build this whole new, non-relational, Java-based beast?
It really comes down to the physical limitations of how relational databases process information. In a traditional SQL database, to ensure data integrity, the system often has to lock entire tables or perform complex joins across multiple tables when writing or reading.
Which is fine on a small scale.
Exactly. At a small scale, this happens in microseconds. But when you distribute a relational database across 1,000 servers, those locks and joins become a massive bottleneck. The servers actually spend more time waiting for each other to finish tasks than they do actually reading data.
Oh, so HBase sacrifices that complex relational logic to prioritize raw speed.
Yes. It strips away the rigid relational structure, the foreign keys, the complex joins, to optimize for pure input-output latency and really high throughput.
So you query it differently then?
Yeah, you don't use native SQL natively.
Yeah.
You write programmatic queries in Java using MapReduce.
MapReduce being the concept where you take a massive query, break it into tiny map tasks, send them to the individual servers to process their local data, and then reduce all their answers into one final result.
Yes. It parallelizes the work, so the massive amounts of data don't have to actually travel across the network to be computed.
Which saves a ton of time.
Exactly. Now, I should mention, if you really want that SQL syntax, there are external projects like Apache Phoenix that provide a SQL layer on top, translating your commands into what HBase understands, but the core engine itself is non-relational.
Let's do a reality check, though. The texts are clear that HBase isn't a universal solution for every big data problem out there.
Right, technology evolves, and different architectures suit very different specific needs. Facebook famously elected to use HBase for its messaging platform back in November 2010.
Which makes sense for chat messages.
It was the perfect tool at the time for ingesting massive amounts of sparse chat data. But by 2018, their internal needs had shifted, and they actually migrated away from it to a system called Myrox.
Interesting.
Yeah. So HBase is a specialized heavy machinery tool. It's not a Swiss Army knife.
Okay, so for the companies that do rely on this heavy machinery, how does it actually run? Because we need to move from the abstract idea of a database to the actual physical architecture. Orchestrating thousands of machines sounds like a logistical nightmare.
It is, and it requires a strict hierarchy. Let's look at the components from the reference guide. At the very top, you have the HMaster.
Okay, the HMaster. I kind of picture it like a massive restaurant kitchen or maybe the dispatcher at a huge shipping company. It doesn't actually drive the trucks or load the boxes. It just monitors the map, tells the trucks where to go, and handles the high-level routing.
That is a highly accurate way to look at it. The HMaster handles assigning what HBase calls regions. A region is simply a chunk of your total data, say, all the user profiles starting with the letters A through C.
Got it.
And the HMaster assigns that region to a specific machine.
And those machines doing the actual heavy lifting are the region servers, like the line cooks in the kitchen.
Exactly. The region servers are your line cooks and your workers combined. These are the nodes that physically manage the data, read it from the hard drives, write new data, and serve it directly to the clients.
Wait, so the HMaster doesn't touch the data?
No. Once the HMaster tells a client which region server holds their data, the client talks directly to that server. The HMaster gets completely out of the way.
But in a cluster of thousands of machines, hardware fails constantly, right?
Yeah.
Network cables get unplugged, power supplies blow out. If a region server dies, how does the system know?
It relies on a required external service called Apache ZooKeeper. ZooKeeper acts as a distributed consensus mechanism. Think of it as an expediter in your kitchen analogy, or a dead man's switch for the entire cluster.
Okay.
Every single region server and the HMaster itself must maintain a continuous heartbeat connection to ZooKeeper. They do this by creating what's called an ephemeral node, basically a temporary digital token in ZooKeeper.
So as long as the server keeps checking in, the token stays alive. But the millisecond the server crashes and stops sending that heartbeat, the digital token just vanishes.
Yes, and when that token vanishes, ZooKeeper instantly alerts the HMaster. The HMaster sees the region server is dead, takes the regions that were assigned to it, and redistributes them to healthy servers.
Wait, what if the dispatcher dies? If the HMaster crashes, the whole system loses its brain. Does the whole restaurant shut down?
What's fascinating here is that the HBase architecture expects the brain to die.
Really?
Yeah. You can run up to 9 backup HMasters simultaneously.
9.
Up to 9. They sit completely idle, doing nothing but watching the primary HMaster's ephemeral token in ZooKeeper. If the primary HMaster crashes, its token vanishes. The backup HMasters immediately see this, and they use ZooKeeper to elect the new leader.
Oh, wow.
The new HMaster steps up in milliseconds, and the rest of the cluster barely notices the hiccup.
That is wild. Setting up this environment isn't just about installing software, though. The physical environment itself has to be perfect. The reference guide explicitly welcomes new users to the, quote, wonderful world of distributed computing, and then immediately warns them that it is hard.
Very hard. They say it is hard because the operating system of every single machine must be tuned to highly specific parameters, or the entire cluster will just spontaneously fail.
Give me an example.
Take NTP, the Network Time Protocol. In a distributed system, you have dozens or hundreds of machines. Their internal clocks must be perfectly synchronized down to the millisecond.
Because HBase relies on timestamps to manage data versions, right? When you overwrite a cell in HBase, you aren't actually deleting the old data. You are just writing a new version with a newer timestamp.
Exactly. When you ask for data, HBase gives you the version with the most recent timestamp. So if machine A thinks it is noon, and machine B's clock is skewed and thinks it is 5 seconds past noon.
Machine B will write data that technically lives in the future.
Right. It will overwrite machine A's genuinely new data because the timestamps are completely out of sync. Your data integrity unravels over just a few seconds of clock skew.
The other environmental requirement that really caught my attention in the manual was the U limit, which is the limit on open file descriptors. A standard Linux installation usually limits a user to opening 1,024 files at once, but the manual states HBase requires at least 10,000, and often more like 10,240.
Yeah, that catches a lot of administrators off guard.
I was trying to figure out how one database is opening 10,000 files simultaneously.
Well, to understand the math, we have to look at how HBase structures its storage. Data in a table is grouped into what are called column families.
Okay.
You group data that is usually accessed together. So for a user, you might have one column family for profile info like name and email, and a totally separate column family for activity logs.
Because if I just want to load their profile picture, I shouldn't have to load 10 years of their click history into memory.
Exactly, that is the principle. On the hard drive, every column family gets its own set of physical files, called store files. So multiply the number of column families by the number of store files.
Right.
Then, remember that a single region server might be managing 100 different regions of data. So it's column families times store files times 100 regions. Suddenly, 1,024 open files isn't nearly enough.
And if Linux refuses to let HBase open more files...
The database just hard crash.
Wow. But the most fascinating failure scenario mentioned in the sources is related to that ZooKeeper heartbeat we talked about earlier, the zookeeper.session.timeoutconfig. By default, it is set to 90 seconds. So ZooKeeper is waiting for a ping. If 90 seconds pass, ZooKeeper assumes the region server is dead. But the server might not be dead at all. It might just be cleaning itself.
This is a classic ghost in the machine. Because HBase is written in Java, it relies on the Java Virtual Machine, or JVM. Java manages memory automatically using a process called garbage collection. It periodically sweeps through the RAM, finding data that is no longer needed, and deletes it to free up space.
But to do a really deep clean, the JVM often has to pause the entire application so the data doesn't change while it's sweeping, right?
Yeah, it is called a stop-the-world pause. If your JVM is poorly tuned and you have hundreds of gigabytes of RAM, that garbage collection cycle might actually take 2 full minutes.
Oh, man. So the server is completely frozen, unable to send its heartbeat to ZooKeeper.
Exactly.
So ZooKeeper hits the 90-second mark, declares the server dead, and tells the HMaster to panic and redistribute all the data.
And then the HMaster kicks off a massive recovery protocol, putting a huge strain on the network. And then, like 30 seconds later, the original region server finishes its garbage collection, wakes up, and wonders why all its data is gone.
That is wild. It is a completely unnecessary self-inflicted crisis caused solely by a memory cleanup routine.
Yeah, it happens more often than you'd think.
So assuming you survive the garbage collection, the clocks match perfectly, and the U limits are high, how does HBase actually process the fire hose of incoming data without choking? If it's handling millions of writes a second, it can't be writing directly to a hard drive. Randomly writing tiny bits of data all over a physical disk is incredibly slow.
You are touching on the core of its ingestion engine here. When new data hits a region server, it is first written to a write-ahead log, a sequential safety net on the disk, just in case of power failure.
Okay, a safety net.
But the actual data you query goes directly into memory, into a space called the MemStore.
So it pulls the data in RAM, but RAM is finite. Eventually that MemStore fills up.
It does. There is a strict configuration monitoring this. When the MemStore hits its limit, HBase takes all that accumulated data and flushes it down to the disk as a single sequential file, called an HFile.
And sequential writing is incredibly fast, which is why HBase can absorb data so quickly. So what does this all mean for the big picture, though? I see an architectural tension here. If you are constantly flushing full memstores to disk, day after day, you are going to end up with thousands of these little isolated H files scattered all over the drive.
Yes, you are.
When a user actually queries the database, the server has to check every single one of those little files to piece together the answer. That fragmentation would destroy your read speeds.
That is the fundamental trade-off of this design, what is known as a log-structured merge tree architecture. You optimize for lightning-fast writes, but you create a fragmented mess for your reads.
So how do you fix the mess?
To solve this, HBase acts as its own janitor, using background processes called compactions.
It cleans up its own fragmented files.
It continuously monitors the storage. It runs minor compactions where it grabs a few of those small, recently flushed H files and merges them into a slightly larger file. And then there are major compactions. In a major compaction, HBase takes every single file in a region, merges them together, drops any deleted data, and rewrites them into one giant, perfectly optimized file.
Wait, rewriting every single file on the hard drive sounds like a massive tax on the system's input-output capacity?
If we connect this to the bigger picture, major compactions are critical for keeping the system fast, but they consume vast amounts of disk I/O. The reference guide sets the default to run a major compaction every 7 days.
Right.
But it provides a very stern warning to administrators. This must be tuned to happen during off-peak hours.
Because if a massive cluster decides to run a major compaction during peak traffic,
You trigger what's called a compaction storm. All your region servers suddenly start rewriting their entire hard drives at the exact same time. The network and the disks hit 100% utilization.
wow.
The servers become too busy copying files to answer user queries, and the whole system grinds to a halt. Real users start seeing timeouts and errors.
Which brings up the ultimate operational challenge. If you are running Imgure's notification system or Netflix's data pipeline, you can't just turn the database off for maintenance.
No, you definitely can't.
You have to upgrade the software while it is actively processing millions of transactions. It is like performing heart surgery on a marathon runner while they are sprinting.
That is a great way to put it. You manage this through rolling upgrades. HBase adheres to strict semantic versioning, which ensures client-server wire compatibility.
Wire compatibility meaning the literal network messages the remote procedure calls sent by an older version of the software can still be perfectly understood by a newer version. They basically speak the same network language.
Precisely. Because they speak the same language, you can upgrade the cluster node by node. You gracefully shut down one region server. The HBase Master temporarily moves its data elsewhere. You update the binary file on that server and boot it back up.
Okay.
You do this hundreds of times, leapfrogging across the cluster with zero downtime for the actual users.
Here's where it gets really interesting, though. The manual outlines a terrifying scenario if an upgrade introduces a critical bug and you need to go backward. It draws a very harsh line between a downgrade and a rollback. Could you explain the difference there?
Yeah, it is a distinction that dictates whether an administrator keeps their job, honestly. A downgrade means you are reverting the software to the older version, but you are keeping all of the new data that was written by the users while the new software was running. You step back the code, but preserve the history.
A rollback, on the other hand, is the nuclear option.
A rollback means you are reverting the entire cluster to its exact state from before the upgrade started. You lose all changes, all transactions, and all user data that occurred in the interim.
Oh, man.
Furthermore, the manual warns that doing a rollback completely destroys all your replication peers.
The replication peers being your backup clusters in other geographic data centers. So you aren't just blowing up your main database, you are breaking the synchronization with your disaster recovery sites.
Yeah, you are effectively blinding your entire disaster recovery infrastructure until you can manually rebuild it.
The manual cites a real-world disaster regarding this. HBase release 1.7.0. What exactly went wrong there to force a rollback scenario?
So, version 1.7.0 introduced a broken compatibility contract for table metadata serialization. Serialization is how the database translates its internal memory structures into a format of bytes that can be saved on a disk or sent over a network.
Okay, so imagine we are passing notes in English. Suddenly, I upgrade and start writing my notes in shorthand Russian. If I downgrade back to English, I can still read your old English notes. But if I wrote core structural data in Russian during that time, you are completely locked out.
That is exactly what happened. Version 1.7.0 changed the language used to write the core descriptions of the tables themselves. Once a 1.7.0 server wrote metadata to the disk, the older versions of HBase literally could not read the alphabet anymore.
Wow.
A safe rolling downgrade became structurally impossible.
So they had to withdraw the release entirely. If you had installed 1.7.0, you couldn't gracefully downgrade. You had to shut the entire cluster down, boot every user offline, and manually fix the serialization formats.
It really highlights how fragile the illusion of seamless technology really is.
It totally changes how you look at your phone. When you mindlessly scroll through Pinterest or wait for an Airbnb listing to load, it feels like magic. But underneath that glass screen, you are relying on an incredibly delicate, heavily orchestrated dance.
Oh, absolutely.
You have MemStores filling up in RAM, ZooKeeper nodes ticking away with 90-second stopwatches waiting for a Java garbage collection to finish, and massive compaction engines waiting for the dead of night to rewrite physical hard drives. It all has to work flawlessly in the background.
It is a breathtaking feat of engineering, and it's driven by a very specific philosophy about data, which actually leads to a fascinating puzzle mentioned early in the Wikipedia article regarding the CAP theorem.
Right. The CAP theorem stating that a distributed data store can only guarantee 2 out of 3 things: consistency, availability, and partition tolerance.
You basically must choose your compromise. The text notes that HBase is strictly a CP system.
CP meaning it prioritizes consistency and partition tolerance over availability.
Exactly. If the network splinters say a fiber optic cable is cut and half your servers lose contact with the other half, HBase will literally block your read request.
Wait, it chooses to go completely offline rather than risk serving you a stale or incorrect piece of data from an isolated server? It refuses to lie to you.
It absolutely refuses to lie. But think about the modern consumer expectation here. We demand 100% uptime from our applications. We complain if a page takes 3 seconds to load, let alone if the server flatly refuses to connect.
That is so true. So the question is the HBase philosophy of correctness over availability a dinosaur of the early internet? Or is that strict, uncompromising demand for consistency the only way we can truly trust our digital infrastructure as it scales to manage our entire lives?
It really forces us to ask what we value more: a system that is always on, or a system that is always right.
That is definitely something to think about the next time your app tells you it can't connect to the server. Maybe it isn't broken. Maybe it's just trying to protect you from bad data. Because down in the depths of a 2 billion record database, finding the truth is hard enough without the system lying to you.
It's definitely something to think about. Thank you for joining us on this deep dive. Keep exploring, stay curious, and we'll see you next time.